Okay, section 3.3, part 3, our last example of linear programming goes back to the one with the saddle mine and the horseshoe mine that we set up in section 3.2. We're doing this one so that we can see a minimum cost in an unbounded region as an example. So if you remember, right, we let X be the number of days that the saddle mine was operated. Y was the number of days that the horseshoe mine was being operated. Our objective was to minimize the cost. It was $14,000 a day for one mine, $16,000 a day for the other mine. That's subject to, and one of these equations was the gold equation. The other one was the ounces of silver that we were producing. But there's our objective and our constraints. We'll start off again, meeting the X and Y intercepts in order to be able to graph them. I'm going to label this as line 1 and line 2 just to help us out. So when you figure out your X and Y intercepts, you're going to find out for line 1 that the X intercept is at 13, the Y intercept is at 8.67. Now, if I end up having to use that as a corner point, I'll convert it back into a fraction so I don't have decimal errors with the rounding on that. The bottom one comes out much nicer in terms of its intercepts. The X-intercept is at 6 and the Y-intercept is 18. So I need to go up to 18 again on the Y-axis. Okay, I'll count by essentially ones, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. 1, 2, 3, 4, 5, 7, 8, 10, 15. Oops. Okay. So 13 and 8.67. So here's 8, 9, like that. On the Y-axis, we're going to come in and cut it through. Now this time when we test the origin, 0 is not bigger than 650. So instead of shading towards the origin, we're going to shade away. And I know that because it's a cost function. We usually don't have things limiting the cost, unfortunately. For the other one, we're going to cut through on the X-axis at 6, and on the Y-axis, we're at the 18. It does something like that. Testing the origin again, 0 is not bigger than 18,000, so it's going to shade away. We also know that we're in the first quadrant, so we'll tack on our X and Y greater than or equal to 0, and there it is. So for the first time, we're seeing that unbounded region. So all of that is what's going on. So as far as corners go, let's see what we've got. So I don't have the origin at all out here. So I can use this and call it point A. This one will be point B. And down here is point C. We know A. A was up there at 18, so it's at 0, 18. And we know C, because it's our other intercept for the other line, which is at, what, 13, comma 0? B is the one we don't know. We have to go solve that system. Again, that's why we waded through all of chapter 2, is to be able to do that. So B is where our two lines intersect. Again, this was, I erased it and I didn't mean to. 1 and 2. We need to get something to cancel here. So let's cancel those X's out. So if we multiply this by 60, we should get 3,000, right? So 50 times 60 is our 3,000. Yep. So we're going to multiply A by a negative 60 times equation 1. So that will give me a negative 3,000x minus 75 times 60. Comes out to be 4,500 equals, again, take out the inequalities. 650 times 60 is negative 39,000. And we'll take the second equation the way it is. So again, that's equation 2. Whoops, I dropped my y. Okay, adding those guys together, we're going to get a negative 3,500. Y equals what? A negative 21,000, and then we'll divide. So 39,000. Just double checking arithmetic. Equals divided by 3,500 comes out to be 6. Y equals 6, which doesn't look half bad. Plugging that back in, I'll go for equation 1. We know that 50x plus 75y, but y is now 6, has to equal 650. So 50x plus 75 times 6, which is 450, equals 650. So 50x equals 200 and x equals 4. Not as good. Well, no, still not bad. But that gives me my other corner, which is really nice. So we now know B is at 4, 6. So now that we have the corners of our region, our unbounded region, let's come in and plug them into that minimum cost function in order to pick out the smallest cost. And it'll tell me how many days to operate each of my mines. I'll build that table. Just helps me organize and stay organized. So here's our corners. And then here's our cost, which was 14,000x, 16,000. Okay, so we had A, which was up there at 0, 18. We have B, which is 4, 6. And then we have C, which is 13, 0. So our cost here is going to be 0 plus 16,000 times that 18. Our cost here is going to be 14,000 times 4 plus 16,000 times 6. Our cost down here is going to be 14,000 times that 13 plus 0. And if you do that, let's see, 0.18 comes in at 288,000. That is sitting there. The 4, 6 comes in at 152,000. And then finally, the 13, 0 is 182,000. Now I know that the examples that we've worked, this point where the baseline seem to intersect is our objective, our maximum or our minimum. That's not always true. It's just the examples that we picked that are the nice cases to start. So we need to finish off our problem. This time we're minimizing. So we're not picking the biggest one. We're picking the smallest one. So we're going to operate the saddle mine 6 days and the horseshoe mine 4 days at a cost of 152,000. And there it is. Now you've seen a minimum. You've seen examples of both a maximization problem and a minimization problem. And that wraps up chapter 3 for us.